the last class, so we are discussing about that why domains form. So what we saw is that we have a interaction, the total energy is a function of magnetostatic plus domain wall, and the magnetostatic wants that the magnetic flux lines which are going out in a single domain state, so they should be confined as much as it can, so that magnetostatic energy will decrease. So if this decreases, so it will create domains, so it forms domains, and that's how it forms domain walls, which will give a positive contribution to energy. So that means it is a balance between the magnetostatic and the domain wall energy, which leads to a equilibrium configuration or domain configuration. So the next question was how the domain walls, how do they look like? So actually there are many ways how, when you look at this, for example, so here this is a 180-degree domain wall, right? So that means the magnetization is turning 180 degrees. So that is a 180 domain wall. There can be also a 90-degree domain wall, 45 degrees, so different angles are possible. Okay? So different angles can be possible. So let's say if I do like this, so this is like a 45-degree, 90-degree domain wall. This is a 90-degree domain wall. So different angles can be possible. But how the magnetization changes across this domain wall, so I will just show it in the presentation here. I will share that so that it is clear to you. Okay, so this is the domains, and we have this breaks up into domain. So single domain, the figure A, which breaks up into domain and domain walls. So this is basically two kinds of domain walls that is possible. So one is called a block wall, and another is a nail wall. So in a block wall, what you see here is, so you have, let's say it's a 180-degree domain wall, and the magnetization in the domain wall is along this perpendicular to the z-axis. So if we say this is the z-axis, so this is the thickness or the width of the material, so it is perpendicular to that. But in a Neal domain wall, the rotation is in the plane, same plane. So here, so you see the magnetization is pointing up and down, but here it is pointing left or right. That is the difference between the block wall and nail wall. So this is again another representation. So again, the block wall, you see the magnetization is pointing up and down in this figure, but here it is only, it's again left to right, pointing left or right. So normally the block wall is the most general what you observe in your most materials, your bulk materials. But many applications nowadays depend on that you thin down your material, so you make thin films. Okay, so you reduce the dimension, so you have X and Y and Z. So let's say you reduce in one direction and make it very thin. The sample can be of a few nanometer, or let's say 10 nanometer or 20 nanometer thick. In that case, you normally observe this nail wall. Okay, so nail wall is observed mostly for thin films and very when the dimensions are small. But normal, any everyday magnetic materials will always have a block wall kind of situation. So this is another representation if you want to look from the top. So let's say you are looking from the top of the surface. So these views are from the side. Okay, so this is you are looking from the side, so the cross section. So now you are looking from the top. So again, the block wall you see here, the magnetization is pointing up, and here the magnetization in the wall. So it is basically rotating in the plane. So these are the views. So you can get a idea how the magnetization changes from one orientation. This transition happens from one orientation to the other orientation. So this is basically your two different domain walls. Okay, so this is again another representation, like a 3D representation of the block wall. So as you can see, the magnetization is kind of lifted out of the axis. So it is making an angle phi, and then gradually, so this angle phi increases and it becomes 90 degree, and then again it goes to the other way, and then you get to the 180 degree rotation. So most of the domain walls actually fall into these two categories. So there are some variation of this, but mostly categorized into these two kind of domain walls. So block wall and nail wall. So definitely they all have certain length or certain width. Okay, we will not do the calculation of that, but just so that you know that these kind of domain walls actually exist in magnetic materials. So this is again, when you apply a magnetic field, basically you move the domain wall, and that is how you get a hysteresis. Okay. So this is one hysteresis loop I wanted to show you. So when you measure the hysteresis along the EG axis or along the magnetization axis, so that is a one. So one is EG axis, one is hard axis. So we'll discuss that. Okay, this I will share it with you so that you can have a look afterwards. And I stop sharing and we go back to the board. So when we look at this domains, okay, so you have, let's say this is your EG axis. Now, if you measure the hysteresis loop along this axis, so you apply a field along this. So this is, let's say, Z axis. And I am applying a field along Z axis, and my EG axis is the Z axis. And I do a hysteresis measurement, so I will get something like this. Okay, so I get something like this. So now, let's say I apply, so instead of that, I apply along, let's say this is my x-axis. So now, so this is my M or B, this is my H, and this is what along Z-axis. So if I apply along H-axis, the same sample, so it will look something looks different. Okay, so something like this. So it is tilted and doesn't really show a real hysteresis loop. Okay, so not very much like a normal hysteresis loop. So this is called a